All we're going to do today is 2 more examples of a write-up. We got to look at what happens if you're not, if you're given data. So if you're not given like a X bar, T, that's what the first one is. What happens if you're given data? And then the second one is just another example, just to go over it again. So just 2 more examples. So a local soda factory, the machines are programmed to fill each can with exactly 12 ounces of soda. Every hour, a random sample of 9 cans is selected, and the average volume is calculated. If the mean is significantly different than 12 ounces, the machine is stopped and adjusted. Here's our one particular sample. So, if you're given data, it's automatically a T. So this is going to be a T test. So if you're given data, it's I wouldn't give you the population standard deviation and then give you a sample. Okay, so you can that's kind of nice. So when we check our conditions, condition 2 is going to change. So first one, do we have a random sample? Yeah, we're good. Next bar is from a random sample. Now condition 2, you don't have n is greater than 30, but we're given data. So I'm going to put my 9 numbers in my calculator under list 1. 12. And you want to do this anyway because then you're going to be able to find all the information for your formula from this also. So what we got to do is we're going to draw a box plot. What you're looking for in the box plot is that it looks symmetric and there are no outliers. We're okay with 1, but we really don't want any outliers. Then you can say the population is approximately normal. So I'm going to turn my scatter plot on. Go to the box plot that's number 4, the first one with the outliers. List 1, pick your whatever you need, and then get out of there, hit zoom 9. No, I have 2 box plots on. So, this is not a good one. If you hit trace, you can see all of, well, the problem is the numbers are so close together, right? I mean, this is only going from 11.98 to 12.1. So it's really not that. Let's see if I change my window. That's not what I want. That's what I wanted. That's really not what I wanted. Yeah, so it's kind of weird. I'll just hit zoom 9. So, this is what you write. So 9 is less than 30. However, a box plot of the distribution is, now we're going to pretend this actually looks nicer than it does, because on the quizzes and tests it will, is approximately symmetric with no outliers. Therefore, we can assume our population distribution is approximately normal. And then you got to draw me a sketch. So notice I put population here Remember, whenever you're doing central limit theorem, you use sampling. When you're doing a box plot, you want population. And then you just draw yourself a little sketch. This one's really not good. You can hit the trace button to kind of help you in terms of where everything is. Okay. Obviously, the ones like on the test, if I give you one of these, it should be approximately symmetric. So that's what you're looking for. It doesn't necessarily have to be perfectly normal, but you really actually don't want what this looks like. Okay, so condition 2 is kind of annoying. But, like I said, they're not going to give you, like, even on a test, if I give you 2 write-ups or 3 write-ups, I'm only going to give you maybe one of these. I'm not going to give you all of them where they all have data. So this is a 1 sample t-test for mean. And our mu is the true, what are we looking at? Mean amount of soda in each can. So for the testing your null hypothesis, you want the mean to be 12 ounces. What's our alternate? What are we at? What are we looking at? Significantly different would just be not equal, so less than or greater than. So this is a two-tailed test. And then we're going to have 2 different t-values. So for our test statistic, usually you list all your stuff. Well, this one's going to be weird now. You actually have to do everything in the calculator first and then write it all out. So when you go over to your test, your t-test, so far we've been doing the stat side where we plug everything in. Go to the data. So your mu sub 0 is still, we're looking at 12 ounces. And then tell me what list all your stuff's in. And then frequency here is 1. And then we're doing a not equals. So on this particular case, it's better to hit calculate than it is to hit draw. Because remember, draw only gives you t and p value. We got to know the x bar, the s, all that stuff. So for this one, you're gonna want to hit calculate. So that's your t, that's your p, but then here's all my information. So x bar is 12.017. S is 0.039, N is 9, degrees of freedom is 8. Then put your formula in. 12.017 minus 12 divided by 0.39 divided by the square root of 9. And you get 1.28 and a p-value of 0.236. Oh, we didn't give an alpha. That's okay. Yes.
You don't put 0.05?
We could, because it really doesn't matter, right? Neither one is worse. But this is greater than all 3, so it really doesn't matter. So t-value of 1.28 gives us a p-value of 2.36 with 8 degrees of freedom. Yeah, if there's no alpha value listed, you still can do everything. A lot of people on the quiz yesterday were talking about there's no alpha values, that's why you can't do a hypothesis test. No, you can still do one. Just what should happen is the p-value should be greater than all three or less than all three. Okay, so here, because our p-value is greater, we're going to fail to reject. So our conclusion, since our p-value of 0.236 is greater than any alpha, we have evidence to fail to reject the claim that the true mean amount of soda in each can is 12 ounces. The question is, should the machine be adjusted? No, because we're going to stick with that it is putting 12 ounces of soda in each can. So it appears the machine should not be adjusted. Okay, your second sentence, either stick with the ho or the ha, or answer the question. Answer the question. So, like I said, these are the most annoying, because you got to do condition 2 is kind of annoying to do, but it's just like it's the same process. Oh, I forgot to do this. T equals negative 1.2.8 and positive. Oh, I don't think I took off on the quiz if you didn't put that in there. Just as long as you had a general picture. Okay, questions on that right up. So we got one more, just to kind of bring it all together. And we're going to talk about statistically significant values. Are students doing better on the SAT math? Suppose that the 2000-2001 school year, the average SAT math score was 573. Based on a random sample of 13,000 scores to date, the average was 575 with a standard deviation of 121. Have SAT scores increased significantly? So we're going to talk about this word. So again, first thing you want to figure out, especially with means, is it a T or a Z? Do you think the standard deviation is for the population or for the sample? The sample. So again, this is a t-test. Okay, more often than not, you're going to have a t-test. So your conditions, X bar is from a random sample. This one's nice. 13,000 is greater than 30. Therefore, our sampling distribution is approximately normal by the central limit theorem. And again, it's a one sample t-test for mean. And mu is the true mean SAT math score. Okay, for your testing, your null hypothesis is that the mean should equal 573. Your alternate, it's asking, has the SAT scores increased significantly? So we're going to go with a greater than. So mu is greater than 573. So this is one-tailed right. Okay, for your test statistic, remember, list everything. So X bar was 575, S was 121, N is 13,000, degrees of freedom is 12,999. We don't have an alpha. Do we have an alpha? No. See what happens with that. So T is 575 minus 573 over 121 divided by the square root of 13,000. Okay. So this time go to your t-test, but again go over to stats. So this was 575. No, 573. X bar is 575. 121. 13,000. And we're doing a greater than. Now again, you can either calculate or draw it. It will still draw if you have something in your scatter, if your scatter plot's still on. So you get T is 1.8846. Our p-value is 0.0298. So let's write out our sentence. A t-value of 1.8846 gives us a p-value of 0.0298 with 12,999 degrees of freedom. Okay, so here's the problem. There was no alpha. So, do we think either error would be worse? Not really, right? Like, saying that SAT results have been increased when they haven't. Saying they haven't been increased when they have. So, I'm going to stick with alpha of 0.05. I'm going to go down the middle. Since neither is worse. So, if alpha is 0.05, we're going to reject because the p is lower than our alpha. Okay. So our conclusion. Since our p-value of 0.0298 is less than our alpha of 0.05, we reject the claim that the mean SAT math score is 573. Question says, have SAT scores increased significantly? It appears, that's what we're going to answer, that SAT math scores have increased significantly. So, when the results of a study are unlikely to happen by chance alone, we call these results statistically significant. So, whenever we reject the null hypothesis, we have statistically significant results. Now, that does not mean that they're practically significant, right? If we really thought SAT math scores have increased, we could change the way we're doing something, but maybe not, right? It's not really a big deal, even though it's significantly, I can't, this is a typo. When the sample size is large, even a very small difference between the observed value and the hypothesized value will give you significant results. So the fact that our sample size here was 13,000 people is really what made the difference. So and then make a note here. Some people are bothered by the fact that different alpha would lead to different conclusions. Like if I did an alpha 0.01, we would fail to reject here. That's just the nature of the process, right? You're controlling the probability of being wrong when you select the level of significance. So you just have to realize that. You can still pick a different alpha if you want. Okay. So that's it for 10.4.